Two-dimensional elements in FEA offer a powerful balance between accuracy and efficiency. But to use them well, we need to understand how they are formulated and when they are appropriate to use. Hi, I'm Dr. Iman. Welcome to section 4 of the FEA Done Right video series at MechCADemy. In this section, we journey through the theoretical background of 2D elements. By working with 2D elements, we can approximate fields over areas. But what about 3D elements? 3D elements are the final frontier. However, before jumping into 3D, mastering 2D is crucial. Nearly every fundamental principle, from shape functions to stiffness matrices and load vectors, generalizes naturally from 2D to 3D. So by learning 2D well, you'll already be equipped to handle 3D when the time comes, without getting overwhelmed by unnecessary complexity. Now, starting from this video, I also want to introduce one FEA reference book in each video. The goal is simple. If you want to dig deeper into the theory behind what we discuss, these books can help. Today's book is Concept and Application of Finite Element Analysis by Cook, Malkus, Pleshaw, and Witt. This is a classic finite element reference. It is useful for senior undergraduate students, graduate students, and practicing engineers. This book covers the theoretical foundation and practical applications of the finite element analysis. So, if you want to go beyond this video and understand the method more deeply, I definitely recommend taking a look at this book. Okay, let's begin our journey in transition from 1D to 2D elements. A good starting point is to recall the shape functions for a one-dimensional spring element. We started by assuming a linear approximation for the displacement field. Displacement u is equal to a1 plus a2x. This is a simple and effective guess. When we express this in matrix form, we have u of x equals to the shape function matrix n multiplied by the vector of the field variables a. Now, matrix n has two elements, n1 and n2. The shape functions for node 1 and node 2. n1 is equal to 1 minus x divided by L, where L is the element length. And n2 is equal to x divided by L. These shape functions are based on an element that spans from x equal to 0 to x equal to L. More generally, if our element spans from node I located at xi to node j located at xj, the shape functions take the following forms. Ni is xj minus x over xj minus xi. And nj is x minus xi over xj minus xi. These functions ensure that when x is xi, ni is 1 and nj is 0, and vice versa when x is xj. This interpolation is the foundation for constructing stiffness matrices and for approximating fields in the finite element method. Now, let's see how we can use this process for a two-dimensional element. One important requirement here is the knowledge of basic matrix algebra, because we will perform many matrix operations. So, buckle up, it's going to be a fun ride. The simplest two-dimensional element is a three-node triangle. Here you see the element with its nodal positions defined in global coordinates. Each node has 2 degrees of freedom. Translation u in the x direction and translation v in the y direction. To approximate the displacement fields, we again assume a linear function. Yes, very similar to the spring element, but this time we have both x and y. So the displacement u is equal to a1 plus a2x plus a3y. And the displacement v is equal to a4 plus a5x plus a6y. So now, both displacement components depend on 2 spatial variables. This is written in matrix form for u as a row vector consisting of 1, x and y multiplied by a column vector of coefficients a1, a2 and a3. By applying the nodal displacement at the 3 nodes, we build a system of equations. For example, at node I, the displacement ui is equal to a1 plus a2xi plus a3yi. And we repeat the same process for nodes j and k. We then write all of these equations in a matrix form. And finally, we find the coefficient vector using matrix algebra. Now that we have all the coefficients, we plug the coefficient vector back into the displacement equation we wrote here on top. As a result, we obtain a final expression for u as a function of x and y. This displacement can now be expressed using shape functions ni, nj, and nk. These shape functions are linear in x and y. They ensure that the displacement u equals the nodal value at each corner of the triangle, because the shape function for each node is equal to 1 at that node and equal to 0 at the other nodes. And yes, we have 3 shape functions because we have 3 nodes. Here we expand the derivation of the shape functions for the triangular element in global coordinates. After rearranging the terms, the shape functions ni, nj, and nk can be expressed in this general form. For example, the shape function ni is written as m11 plus m21x plus m31y. Now these coefficients are calculated using the formulas shown here. For example, m11 is xj yk minus xk yj, all divided by 2a, where a is the area of the triangle. Next, m21 is equal to yj minus yk over 2a. And m31 is equal to xk minus xj over 2a. And similarly, we compute the remaining coefficients for nj and nk. I also want to add that the area of the triangle is given by 1/2 times the determinant of the matrix that consists of the nodal coordinates. As you can see, the procedure to find shape functions in global coordinates is not short, but it's straightforward. Now, how about field variable v? Sure, we can repeat the same procedure for displacement v. So we have these separate formulas for u and v. I want you to pay a special attention to the fact that we actually use the same shape functions for u and v, as the derivation procedure is the same for both and the same nodal coordinates are used for them. Now, let's show this in a matrix form. The displacement vector uv is obtained by multiplying a 2 by 6 shape function matrix by the nodal displacement vector. The shape functions matrix here has 2 rows because we have 2 displacement components. And it has 6 columns because each of the 3 nodes contribute 2 degrees of freedom. Now, although the simplest 2D element is the triangular or tri-element, quadrilateral elements are also used widely in practice. So it is important to cover them to build a more comprehensive understanding of FEA. Take a look at this quadrilateral element. For short, it is also called quad. It has 4 nodes and the x and y positions are given in global coordinates. Here we assume bilinear approximating functions. We need 4 terms because we have 4 nodes. U is equal to a1 plus a2x plus a3y plus a4x times y. And similar for v. Even though you see a multiplication of x and y, these approximating functions are still called linear because all powers are either 1 or 0 for each individual coordinate. As long as none of the terms involve squares or higher powers, the interpolation remains linear in this sense. If we take the same procedure we took for tri-elements, we can derive 4 shape functions for the quad elements. Why 4? You know the answer. Yes, because we have 4 nodes in quad element. Now, we saw how tedious the derivation of the shape functions for tri-elements was. Just imagine how much harder it would be for quad element. So normally for this element, the shape functions are given in a local coordinate system. In fact, we have to use local coordinates even for 2D triangular elements, as we have to deal with lots of integrations that are hard, if not impossible, to do using global coordinates. So now, let's talk about the local coordinates. Depending on the element type, we use different types of local coordinates. For example, for tri-elements, we use area coordinates. And for quad elements, we use serendipity coordinates. These local coordinates are dimensionless and always cover a standardized range, like from -1 to 1 or from 0 to 1. That means the shape functions become universal. as they don't change from one element to the next. So the integration process becomes much easier, since the element size and shape are always the same in the local coordinates. In short, local coordinates help transform irregular geometry into a simple and clean algebraic setup, which is one of the main reasons FEA can handle such complex structures with ease. We'll briefly look at each of these coordinate systems in the next slide and see how they help shape functions stay simple and consistent regardless of the element size or orientation. Let's start with a one-dimensional spring or bar element. Here you see the familiar shape functions in the global coordinate system. Now let's introduce a serendipity coordinate called R. For this coordinate system, node I sits at r -1, node j is at r1, and midpoint x bar is at r0. Therefore, this coordinate maps the physical x-axis onto the standard interval from -1 to 1. We do this using the following formula: r equals 2 times x minus x bar over xj minus xi. Now we can rearrange this formula into an inverse mapping as follows: x equals x bar plus 1/2 xj minus xi times r. Now we can write the shape functions we derived in global coordinates for the spring elements in local coordinates using this mapping. So for node I, ni equals 1/2 times 1 minus r, and nj equals 1/2 times 1 plus r. See again, ni is equal to 1 at node I, where r equals -1, and it is 0 at node j, where r equals to +1. Similarly, nj is 0 at node I and 1 at node j. Let me repeat this important statement. This is in fact the defining characteristics of any shape functions. They are 1 at their associated node and 0 at all other nodes. Also, note that linear shape functions vary linearly from node to node. Now, let's view the same one-dimensional element through another local coordinate system called length coordinates. In length coordinate system, instead of a single r coordinate, we attach two variables to any interior point P. Coordinate Li measures how far point B is from node J, and Lj measures how far point P is from node I. Both Li and Lj are non-dimensionalized by the total length of the element. Now we can write Li equals the distance from P to J divided by the distance from I to J. This can also be written as xj minus x divided by xj minus xi, as xp is an arbitrary point. What is this formula? Does it remind you of another one you have seen before? Yes, this is an I. The shape functions for node I we found using global coordinates. Similarly, Lj equals x minus xi divided by xj minus xi, which is equal to nj, the shape functions for node j in global coordinates. Okay, now you can tell what ni and nj in local coordinate system are. Yes, the shape functions are equal to the local coordinates. So simple, isn't it? Now, two important notes. First, each length coordinate varies in the range from 0 to 1, unlike the single serendipity coordinate that changes from -1 to 1. Second, here we have two length coordinates, but they are not independent. As you can see, Li plus Lj equals 1. Now, let's jump to the quadrilateral element. For the 4-node quad element, we switch to serendipity coordinates. This is a 2D element, so we have two serendipity coordinates, r and s. The mapping is shown here. R equals x minus x bar divided by a, s equals y minus y bar divided by b. Here, a and b are the half width and half height of the element. Also, x bar and y bar are the averages of the x values and y values of the nodes. The shape functions can then be derived using the bilinear polynomials we introduced earlier for the quad elements in global coordinates. And I equals 1/4 times 1 plus r times 1 minus s. And so on and so forth for the other shape functions. All four shape functions live in the square where r and s range from -1 to 1. A perfect playground for Gaussian integration. I know this is sudden, but that's me. Sometimes I create a chaos to prepare your mind for what is coming later. For now, just remember that Gaussian integration is where you see the real power of local coordinates in FEA. Now, let me share a fun history here. The term serendipity was coined by Horace Walpole in 1754 after reading the Persian fairy tale The Three Princes of Serendip, whose heroes kept making lucky discoveries. Also in the 1980s Japanese anime Serendipity the Pink Dragon, a boy named Kona finds a friendly pink sea dragon on a mysterious island, again by pure chance. Likewise, there is a guess that early finite element pioneers stumbled upon these tidy RS shape functions while experimenting with normalized coordinates. A fortunate discovery, a serendipity. That's it for a quad element. Now let's go to the three-node triangular element to see how local coordinates are defined and utilized to find the shape functions. It is well established that for triangular and tetrahedral element, area and volume local coordinates are used. These coordinates are also known as barycentric coordinates. Let's focus on the triangular element. Any interior point P is described by three non-negative variables, Li, Lj, and Lk. These variables represent the fractional areas of the three subtriangles opposite each node. For example, Li equals the area of triangle PJK divided by the area of the triangle IJK, and so on and so forth. Again, like we did for the length coordinate system, we can show that Li equals Ni, Lj equals Lj, and Lk equals Nk. And all of them lie in the range from 0 to 1. These coordinates, though, are not independent because Li plus Lj plus Lk equals 1. These barycentric coordinates are perfect for numerical integration. Now, can you guess the shape functions if we use volume coordinates for a tetrahedral element? Yes, those will be like the triangular element, but now we have more shape functions because we have more nodes. Okay, I'm done with the local coordinates for now. I've been waiting to talk about the next topic until now, and now you are ready to digest it. I want to talk about element order. Element order refers to the polynomial degree of the shape functions. So far, shape functions have been only linear or bilinear polynomials. Now we can go one step further and increase the order of the shape functions, but we don't need to increase it by much. Even one additional degree makes a big difference in the solution accuracy. When we increase the polynomial order by 1, we obtain second order elements, also called quadratic elements. Most commercial solvers, including ANSYS Workbench, default to quadratic elements for structural analysis. For illustration here, the left figure shows a linear quad with 4 corner nodes, while the right one adds 4 mid-side nodes, creating a quadratic quad element. Now, here is the polynomial we used before for the linear quad element. And here is the polynomial that we use for the quadratic element in global coordinates. See the quadratic terms here? Also look how many terms this polynomial has. Yes, 8 terms. Why? Because now we have 8 nodes. For this element, we should definitely use local coordinates. For quad elements, we use serendipity coordinates. Here again, the shape functions in serendipity coordinates R and S are shown for the linear element. And here we have them for second order element. For this element, we have 8 nodes, so we have 8 shape functions as well. And all the shape functions are quadratic with respect to at least one coordinate. One more note here. Quadratic terms let the edges of a single element bend, making it much more accurate on curved or bending dominated problems. It is important to note that accuracy improves with element order, but computational cost also increases. A rough rule of thumb is that CPU time grows with the square of the number of the degrees of freedom. In simple terms, if you double the number of degrees of freedoms, the computation can take about 4 times longer. Linear elements like these ones in 2D and these ones in 3D have fewer nodes per element. That makes them faster to assemble and solve. But the trade-off is lower accuracy, especially in capturing curve boundaries or stress gradients. On the other hand, quadratic elements, as are shown here in 2D and 3D, include mid-side nodes and improve accuracy substantially but at a cost. For example, a linear tetrahedral element has a 12 by 12 stiffness matrix. The quadratic version grows to 30 by 30. For hexahedral or brick elements, linear is 24 by 24 and quadratic expands to 60 by 60. That's a big jump in matrix size and consequently in computational time. In practice, linear quads and hexes or quadratic tris and tets often offer a good balance between accuracy and computational efficiency. Okay, this concludes section 4 of the FEA Done Right video series at MechCADemy. We are now ready to answer a very important question in FEA in structural problems. How do we calculate the stresses and strains in FEA? This can be expanded to thermal problems too, but instead of a strain, we have thermal gradient. We cover this in the next section of FEA Done Right series at MechCADemy. See you soon.